Right now, something invisible is tearing the universe apart. Space itself is stretching, accelerating, pushing every galaxy away from every other galaxy faster and faster. Scientists confirmed this in 1998. They still don't know what's causing it. They call it dark energy. It makes up 68% of everything that exists. And quantum physics says empty space should be overflowing with it. Yet the numbers are off by more than anyone can explain. Today we go from the expanding cosmos down to vibrating quantum fields, through phantom energy and cosmic phase transitions, all the way to the edge of what physics can say. If you enjoy the journey, subscribe. We make these for the curious. Ready? Begin. Picture this. You throw a ball into the air. Gravity pulls it back. Every child knows this. Every physicist expects it. So when scientists pointed their telescopes at dying stars billions of light years away, in 1998, they expected to see the universe slowing down. Gravity should be doing what it always does, pulling everything back together. Instead, they found the opposite. The universe was speeding up. Galaxies were flying apart faster than they did 1 billion years ago. Faster than they did 2 billion years ago. Something was pushing outward with a force so immense, it was winning against the gravity of hundreds of billions of galaxies combined. And nobody had predicted it. Nobody had a name for it. Nobody had any idea what it was. They named it dark energy, a placeholder word, a confession that physics had hit a wall. Here is what makes this stranger than it first sounds. Dark energy doesn't behave like any force we've ever seen. Every known force gets weaker with distance. Gravity, electromagnetism, they all fall off as things spread apart. Dark energy does the opposite. As the universe expands and space grows larger, dark energy grows stronger, or at the very least it stays perfectly constant, never diluting, never weakening, always pressing outward at exactly the same rate per unit of space. The more space there is, the more dark energy there is. Imagine filling a room with water pressure. Now imagine the room doubles in size, but the pressure doubles with it, perfectly, automatically. No pump, no source you can point to. The pressure just appears with the space. That's the behavior we're dealing with. And the scale of this is hard to grasp. Dark energy makes up approximately 68% of the total energy content of the entire observable universe. All the stars, all the planets, all the gas clouds, all the black holes, that's roughly 5%. Everything we've ever seen or measured or touched makes up 5%. Dark matter, which we also can't see directly, makes up about 27%. And this unknown outward pressure, dark energy, owns the remaining 68%. Physicists aren't guessing at this. They've measured it through 4 completely independent methods: the expansion rate of the universe, the structure of the cosmic microwave background radiation, the clustering patterns of galaxies, and the brightness of a specific type of exploding star used as a standard measuring tool. All 4 methods agree. Something with these properties exists. Something is driving acceleration. Pause on that for a second. The dominant ingredient in the universe, by a massive margin, is something we cannot detect directly, cannot explain from first principles. Our best models describe its effects with stunning precision. Its nature remains completely open. And here's the detail that should unsettle you. When physicists turn to quantum physics, the most precisely tested theory in human history, for an explanation, the math doesn't just fail to explain dark energy. It predicts a vacuum energy so enormous it should have ripped the universe apart before a single atom ever formed. The theory that explains everything from semiconductors to lasers to the structure of atoms produces a number that is wrong by more than 120 orders of magnitude. That's a 1, followed by 120 zeros. That's the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. Something is deeply, fundamentally missing from our understanding of reality. To find out what, we need to go back further. Back to the moment astronomers first realized space was doing something nobody expected. In the 1920s, most astronomers believed the universe was static, fixed. The stars were where they were, and that was that. Even Albert Einstein, whose equations of general relativity actually predicted a dynamic, changing universe, inserted a fudge factor into his own math specifically to keep the cosmos still. He called it the cosmological constant. He used it to cancel out the expansion his own equations demanded. Then a quiet astronomer in California changed everything. Edwin Hubble was measuring the distances to faint smudges of light called nebulae, objects that many astronomers assumed were just gas clouds inside our own galaxy. To measure their distances, he used a specific type of pulsing star called a Cepheid variable. These stars brighten and dim in a rhythm, and that rhythm is directly tied to how intrinsically bright they are. By comparing how bright they look from Earth to how bright they actually are, you can calculate exactly how far away they are. It works like knowing a streetlight always shines at the same wattage. If it looks faint, it's far. Hubble's measurements revealed something extraordinary. These nebulae were so far away, they had to be entire separate galaxies, far outside the Milky Way, hundreds of billions of stars each, and they were moving. But the motion wasn't random. Every galaxy was moving away from us. The farther away a galaxy was, the faster it moved. This pattern had a name almost immediately: Hubble's law, and the relationship it described had only one clean explanation: space itself was expanding. Here is why that distinction matters. If galaxies were simply flying through space the way a cannonball flies through air, you'd expect to see motion in all directions, some toward us, some away. But almost every galaxy beyond our local neighborhood moves away, and the speed scales precisely with distance. The only geometry that produces this pattern is a universe where space itself is stretching uniformly in all directions, like dots on the surface of a balloon being inflated. Sit with that image. You're one dot. Every other dot moves away from you as the balloon grows. From your dot's perspective, you appear to be at the center of expansion, but so does every other dot. There is no center. Space is simply growing everywhere at once. This means galaxies aren't moving through space to get farther apart. The space between them is stretching, carrying them along. Light traveling between two galaxies actually has to cross more space than it started crossing, because space keeps growing during the journey. That's why distant galaxies emit light in the visible range, but we receive it shifted toward red. The wavelength stretches as space stretches around it. Hubble measured the rate of this expansion. Scientists call it the Hubble constant. It describes how fast galaxies recede per unit of distance. For decades, physicists assumed this rate was slowing down. Gravity, after all, pulls matter together. A universe born in an explosive beginning should be coasting and decelerating. For 70 years, that assumption went unchallenged. Then two teams of astronomers decided to measure the deceleration directly, using the most powerful natural rulers available: exploding stars visible across billions of light years. They expected to confirm the slowdown. What they measured instead rewrote physics. Most people hear the universe is expanding and picture an explosion, a bang, a center, debris flying outward into surrounding empty space. That picture is completely wrong, and the correct one is far stranger. There is no center. There is no surrounding empty space. The universe isn't expanding into anything. Space itself is what's growing, and it's growing everywhere simultaneously. To feel why this breaks normal intuition, try this thought experiment. Imagine you live on the surface of a sphere, a perfectly smooth ball. You walk in any direction for 1,000 miles, and you never reach an edge. There is no edge. The surface curves back on itself. Now imagine that sphere inflating. Every point on its surface moves away from every other point. An ant standing anywhere on that sphere would see every other ant receding. Every single ant would feel like the center of the expansion. And every single ant would be right, because every single point is expanding equally. That's the closest two-dimensional picture of what three-dimensional space is doing. And it's confirmed. Here's the specific thing quantum physics needs to reckon with. If space is a thing, something that stretches, curves, and carries energy, then space itself has physical properties. Space has a geometry. Space responds to mass and energy by curving. Space can wave, as gravitational waves prove. Space can expand, and according to quantum field theory, space can contain energy even when completely empty of matter. That last point is the critical one. Empty space, in quantum physics, is actively doing something. It carries fields. Those fields vibrate. and that vibration costs energy. When space expands, it creates more of itself, more volume, and if that volume carries intrinsic energy at every point, then expansion generates more energy automatically. This is why dark energy behaves the way it does, growing with the volume of space rather than diluting. It would make perfect sense if dark energy is a property of space itself, a fixed energy density baked into the fabric of the universe. But there's a problem hidden in that solution, a catastrophic one. If space carries quantum energy at every point, then quantum field theory can calculate how much energy that should be. And when physicists run that calculation, the number comes out so enormous it's essentially infinite compared to what we measure. The prediction and the measurement disagree by more than 120 orders of magnitude. To put that in perspective, the distance between two hydrogen atoms in a water molecule is about 1 angstrom. The diameter of the observable universe is about 500 billion trillion miles. That ratio, atom to universe, is roughly 25 orders of magnitude. The vacuum energy prediction is wrong by a factor nearly 5 times larger than the ratio of the smallest thing we've measured to the largest structure we can see. This is called the vacuum catastrophe. Physicists consider it the worst quantitative failure in the history of theoretical physics. The math works flawlessly for everything else. Particle accelerators, chemical reactions, transistors. Quantum field theory predicts them all with extraordinary accuracy. Then you apply it to empty space, and it screams an impossible number. Something is cancelling that energy down. Something is suppressing it to almost zero. We don't know what. Before we can understand the vacuum catastrophe, we need to understand what quantum fields actually are, and why even a perfect vacuum seethes with energy. Forget particles for a moment. In the quantum picture of reality, particles are secondary. What's primary are fields. Fields are the fundamental stuff. A field is a quantity that has a value at every point in space, simultaneously. Temperature is a field in the everyday sense. Every point in a room has some temperature value. But quantum fields are different. They're physical entities that fill all of space. They interact with each other, and they can carry energy. Every type of particle we know corresponds to a quantum field. The electron field fills all of space. The quark field fills all of space. The photon field, which we call the electromagnetic field, fills all of space. These fields aren't empty channels through which particles travel. The particles themselves are disturbances in these fields. An electron is a ripple in the electromagnetic field. A photon of light is a ripple in the electromagnetic field. Kick the field hard enough in a small region, and a particle pops into existence. Let the ripple settle, and the particle disappears. Now here's where it gets critical. Quantum mechanics has a rule built into its foundations. You cannot have zero energy. Specifically, the Heisenberg uncertainty principle says that if you know precisely where something is, you cannot know its momentum, and vice versa. If a field were truly at rest, truly zero, you would know both its value and its rate of change simultaneously. That violates the uncertainty principle. So the field can never be zero. It always has a minimum amount of jiggling. Always. That minimum jiggling is called zero-point energy. Every quantum field, in every region of space, even in the deepest empty void between galaxies, carries this irreducible baseline vibration. Picture a guitar string. If you cool it to absolute zero temperature, classical physics says it stops vibrating entirely. Quantum physics says it can't. It still hums at its lowest possible frequency. You can't pull the vibration out. It's permanently there, built into the structure of the string by the rules of quantum mechanics. Every quantum field is like an infinite collection of these strings, one at every point in space, each humming at its zero-point frequency, each carrying a tiny but real amount of energy. Multiply that by all the fields we know about, running across all of space, and the total energy is staggering. This zero-point energy is real. It's measurable. We've measured it in the lab. In the 1940s, a Dutch physicist named Hendrik Casimir predicted that two uncharged metal plates placed extremely close together, closer than a hair's width, should experience an attractive force pushing them together, even with no electrical charge, no magnets, no physical contact. The plates would be pushed together by the energy of the quantum vacuum itself. His reasoning was elegant. Between the plates, only certain wavelengths of vacuum fluctuations fit. Outside the plates, all wavelengths exist. The outside has more vacuum energy than the inside, so the net pressure pushes the plates inward. Decades later, experiments confirmed his prediction with high precision. The Casimir effect is real. Quantum vacuum energy physically pushes things. It's been measured. It's in engineering textbooks. It's the most direct confirmation we have that empty space is energetically active. And that confirmation makes the vacuum catastrophe even more urgent. Because if the vacuum energy is real, and if it's as large as quantum theory predicts, the universe should have exploded into nothingness in the first fraction of a second of its existence. Something tamed it, and that same something might be dark energy. Two metal plates, no charge, no magnets, a gap smaller than a human hair, and between them, a measurable force appears from pure vacuum. The Casimir effect sounds like a curiosity. It's actually one of the most profound experimental results in modern physics. It tells us that empty space has mechanical properties. It pushes, it pulls, it responds to geometry. And the energy behind it comes from the quantum fields that fill every point in the universe. Here's a cleaner way to picture how it works. Imagine standing in a room with sound bouncing around at every wavelength simultaneously, a roar of every frequency at once. Now imagine two walls placed close together inside that room. Between those walls, only certain wavelengths fit. The long ones can't squeeze in, they get excluded. So inside the gap, the energy spectrum is missing some contributions that exist everywhere else in the room. Outside the walls, full energy. Inside the gap, reduced energy. That imbalance creates a net inward pressure. The walls get pushed together by the difference. That is precisely what happens with quantum vacuum fluctuations and the Casimir plates. The geometry of the gap cuts off certain modes of the quantum field. The outside has more vacuum energy than the gap. The plates feel a real measurable attractive force. In modern experiments, scientists have measured this force to within a few % of the theoretical prediction. That's extraordinary precision for something arising from literally empty space. The effect is now used as a calibration tool in nanotechnology. Engineers building devices at microscopic scales have to account for Casimir forces the way bridge builders account for wind. Here's the implication that cuts deep into the dark energy problem. The Casimir effect confirms that vacuum energy is physically real and geometrically sensitive. The energy of empty space isn't a bookkeeping fiction in the equations. It actually pushes on matter. So when quantum field theory predicts a vacuum energy density that would overwhelm everything, that prediction has real physical weight behind it. The vacuum isn't passive, and yet the universe exists. Galaxies formed, atoms assembled, life emerged. The catastrophic vacuum energy that quantum theory predicts didn't blow everything apart, so something, somewhere in the physics, is cancelling almost all of it. Something reduces the raw quantum prediction by a factor so enormous it staggers the imagination. Physicists call this cancellation the cosmological constant problem. It's been open since the 1970s. Every attempt to solve it has failed. Supersymmetry was supposed to cancel out the contributions from different fields automatically. But even if supersymmetry exists, the cancellation only works to a point. A large discrepancy remains. String theory offers a different route, through an enormous landscape of possible vacuum states. Other approaches invoke unknown symmetries or new physics entirely. None of them fully close the gap. And here's the layer that makes everything stranger. Dark energy isn't just the raw vacuum energy. It's something far smaller, far quieter. It might be the leftover, the tiny residue after some enormous cancellation we don't yet understand. A whisper after a roar. A single note after a full orchestra falls silent. To understand how physicists first tried to formally describe this whisper, we need to revisit a calculation Einstein made, and immediately regretted. In 1917, Albert Einstein did something unusual. He broke his own equations. His field equations of general relativity, published a year earlier, described how mass and energy curve spacetime, and how that curvature governs the motion of everything moving through it. When Einstein applied those equations to the universe as a whole, they predicted something he found unacceptable. The universe had to be either expanding or contracting. A static, eternal cosmos was mathematically impossible under his own theory. Einstein believed in a static universe. Everyone did. So he added a term to his equations, a constant, a fixed number multiplied by the metric of spacetime, specifically engineered to balance the tendency for gravity to collapse everything inward. He called it the cosmological constant, represented by the Greek letter lambda. It acted like a uniform built-in repulsion spread through all of space, enough to hold the universe steady. Then Hubble's measurements came in. The universe was expanding. Einstein's static universe was wrong. He had added the constant for the wrong reason, and he called it the biggest blunder of his career. The term was removed. Physics moved on. For decades, most physicists assumed the cosmological constant was exactly zero. No term, no repulsion, nothing built into the fabric of space. That was the clean answer. Then 1998 arrived. Two independent teams of astronomers, using dying stars as measuring tools, discovered that the expansion of the universe wasn't slowing down, it was accelerating. And when theorists looked for a physical mechanism to explain it, they found that Einstein's discarded constant fit the data almost perfectly. A small, positive cosmological constant, a fixed uniform energy density built into spacetime, could drive exactly this kind of gentle, steady acceleration. Einstein's blunder had come back from the dead, but now the term needed a physical interpretation. If the cosmological constant is real, what does it represent? One natural answer came from quantum field theory: vacuum energy. The energy of empty space, those zero-point vibrations of every quantum field, would act exactly like a cosmological constant. It would be uniform across all of space, wouldn't dilute as the universe expanded, and would produce a constant outward pressure on spacetime. The interpretation seemed perfect. The math matched. The behavior matched. The problem was the size. The vacuum energy that quantum field theory predicts, before any cancellation, is roughly 10 to the power of 120 times larger than the observed value of the cosmological constant. If you took all the energy the quantum vacuum should contain and compared it to the tiny value we actually measure driving the universe's acceleration, the ratio is a number with 120 zeros. Einstein's constant returned as a solution and immediately revealed a deeper problem. It answers the question of what dark energy does. It acts like a cosmological constant, a built-in property of spacetime that accelerates expansion. It says nothing about why that constant has the precise value it does, instead of the enormous value quantum physics predicts. The gap between those two values is the central mystery of modern cosmology, and several competing theories have stepped forward to explain it. The most creative of them imagines dark energy as a living, breathing field that's been slowly changing since the universe began. What if dark energy isn't fixed? What if it's a field, slow-moving, spread across all of space, and evolving over billions of years? That's the idea behind quintessence. The name comes from the ancient Greek concept of a fifth element beyond earth, water, fire, and air, a subtle substance that fills the heavens. Physicists borrowed the name for a specific proposal. Dark energy is a scalar field, a quantum field, with a single value at each point in space, that started with high energy early in the universe's history and has been slowly rolling downhill ever since. Think of a ball placed near the top of a very long, very gentle slope. It starts high, it rolls slowly. Over billions of years it barely moves, but it does move. The energy it carries, its position on the slope, gradually decreases. If dark energy is this rolling field, then the repulsive pressure it generates changes over time, linked to wherever the ball happens to be on the slope at any given cosmic moment. This single feature separates quintessence from the cosmological constant in a testable way. A cosmological constant is permanent and fixed. It has the same value today that it had 10 billion years ago, and will have 10 billion years from now. Quintessence varies. If the dark energy density was different in the early universe than it is today, quintessence wins over the cosmological constant. This matters because it changes the physics of everything that happened in between. If dark energy was stronger in the early universe, it would have affected how the first galaxies clustered. It would leave fingerprints in the large-scale structure of the cosmos, subtle signatures in how matter is distributed across billions of light years. Quintessence also offers a potential path toward explaining the cosmological constant problem, though a partial one. In some quintessence models, the field naturally evolves toward a small value over cosmic time. The universe starts with enormous vacuum energy, and the field slowly dissipates it. The current tiny value isn't a coincidence. It's where the field happens to be after 14 billion years of rolling. But quintessence introduces its own mysteries. For the field to behave this way, it has to be extraordinarily light, far lighter than any known particle. Its interactions with normal matter have to be incredibly weak, or we'd have detected it directly already. And the shape of the potential energy slope the field rolls along has to be tuned to produce the right behavior over billions of years. Exchanging one fine-tuning problem for another is an uncomfortable position for any theory. Still, quintessence is testable. Astronomers can measure how the expansion rate of the universe changed over time in detail, mapping it across different cosmic epochs. If the dark energy density varied, even slightly, the expansion history will show it. Current and upcoming telescope surveys are designed specifically to hunt for this variation, and that hunt has already produced results that shocked the cosmology community. In 2004, data from a large galaxy survey suggested that dark energy might actually be weakening. If confirmed, it would rule out the cosmological constant entirely. But before we get there, we need to confront the darkest version of this story, because some quintessence-like models don't predict a weakening. They predict something far worse. Most theories of dark energy predict it stays constant or slowly fades. Phantom energy goes the other direction. Completely and terrifyingly the other direction. In phantom energy models, dark energy doesn't just maintain its strength as the universe expands. It grows. The repulsive pressure increases over time. The acceleration of the universe doesn't plateau or slow. It climbs. And if it keeps climbing without limit, the universe ends in an event physicists call the Big Rip. To understand why this is possible, you need to know about something called the equation of state. Every substance in physics has a relationship between its pressure and its energy density. For ordinary matter, pressure is small compared to energy density. For radiation, the ratio is exactly 1/3. For a cosmological constant, the ratio is exactly -1. Pressure is negative, and its absolute value equals the energy density perfectly. This negative pressure is what drives acceleration. Phantom energy has an equation of state below -1. The pressure is more negative than the energy density. And as space expands, instead of the energy density staying constant or dropping, it increases. More space means more phantom energy, which means faster expansion, which means even more space, which means even more phantom energy. A runaway feedback loop that cannot stop. In a universe dominated by phantom energy, this feedback runs forward into the future and eventually reaches a finite time, not infinitely far away, where the expansion rate becomes infinite. Physicists call this the Big Rip singularity. As it approaches, the effects roll inward through scales. Billions of years before the end, the accelerating expansion overwhelms gravity between galaxy clusters. Clusters disperse. Then, closer to the end, the expansion rate grows strong enough to overwhelm the gravity holding individual galaxies together. Galaxies shred apart. Stars scatter. Hundreds of millions of years compress into a tighter timeline as the feedback accelerates. Then planetary systems. Planets get pulled away from their host stars. Individual gravitational bonds break. The timeline compresses faster now. Then the expansion rate overwhelms the electromagnetic force, the force holding atoms in molecules, molecules in cells, cells in everything alive or structured. Matter itself disintegrates, not into smaller pieces, into unbound particles. Then, in the final moments, fractions of a second before the singularity, the expansion overcomes the strong nuclear force. Atomic nuclei tear apart. Protons and neutrons dissolve. The last structures in the universe are quarks flying apart from each other at infinite speed as space-time tears itself to pieces. Current measurements suggest we are probably not in a phantom energy universe. The observed equation of state is close to -1, the cosmological constant value. But the error bars still allow phantom energy, and some models let the equation of state drift across -1 over time, starting in one regime and crossing into the other. This is why precision measurements of dark energy's equation of state matter enormously. A number close to -1 is safe. A number below it, confirmed, means the clock is ticking. And now the question becomes, what is phantom energy made of, if it exists? What kind of field produces an equation of state more negative than a cosmological constant? The answers lead into genuinely uncharted physics, and into one of the strangest proposals ever made about the nature of dark energy. Let's make this concrete. Assume phantom energy is real. Assume the equation of state is slightly below -1 and staying there. Theoretical models suggest the Big Rip would arrive roughly 20 billion years from now. That number shifts depending on the exact value of the equation of state, but the sequence of events is consistent across models. And walking through that sequence reveals just how precisely physicists understand the physics of destruction, even for events that may never happen. 20 billion years from now, the night sky goes dark. Every galaxy beyond our local group has already been receding fast enough that its light can no longer reach us. The expansion carries it away faster than light travels through the space between. Our local group, held together by its own gravity, remains intact for a while longer. But phantom energy's grip tightens. About 1 billion years before the rip, the expansion rate overwhelms the gravitational binding of galaxy clusters. Our local group disperses. Individual galaxies drift apart. The Milky Way and Andromeda, which would otherwise be expected to merge, separate instead. 60 million years before the end, the Milky Way itself is torn apart. Stars that have orbited the galactic center for billions of years drift outward and scatter. The galaxy dissolves into a loose field of isolated stars. 3 months before the rip, the expansion rate has grown powerful enough to unbind planetary systems. Planets are stripped from their orbits around stars. The gravitational links holding star systems together snap one by one. 30 minutes before the end, the expansion overcomes the electromagnetic force at planetary scales. Solid matter, rock, metal, ice, can no longer hold its structure. Objects don't explode. They simply come apart, their components no longer able to maintain contact against the expanding space between them. Fractions of a second before the singularity, the strong nuclear force fails. Atomic nuclei disintegrate. Protons and neutrons, which are themselves made of quarks held together by the strongest force in nature, come apart. The quarks separate. At this scale, space is expanding so violently that even the interior of a proton is being stretched faster than the force holding it together can respond. And then, the singularity, a moment where the mathematics of general relativity produces infinite values, infinite expansion rate, infinite energy density. The equations break down, which means our current physics cannot describe what happens at or beyond that point. What makes this scientifically interesting, beyond the spectacle, is that the Big Rip scenario gives physicists a precision test. The exact timing and sequence depends sensitively on the equation of state of dark energy. Different values produce different timelines. If future telescopes could measure the expansion history of the universe precisely enough to pin down the equation of state to several decimal places, we could calculate whether the Big Rip is in our future, and if so, approximately when. The measurement challenge is extraordinary, but astronomers are working toward it. And meanwhile, some physicists have looked at dark energy from a completely different angle. Instead of asking what substance produces the acceleration, they've asked whether the acceleration might be telling us something fundamental about the relationship between space, information, and gravity itself. That line of thinking leads somewhere deeply unfamiliar. Everything you know about physics operates in 3 dimensions of space and 1 dimension of time. But one of the most striking ideas to emerge from theoretical physics in the last 30 years suggests that everything happening in a volume of space can be completely described by information encoded on the 2-dimensional boundary surrounding that volume. This is called the holographic principle. It grows out of Stephen Hawking's work on black holes in the 1970s, where he discovered that a black hole's entropy, a measure of its hidden information, is proportional to the area of its event horizon, not its volume. A 3-dimensional object's information content is fully captured by a 2-dimensional surface. String theorist Juan Maldacena formalized this into a precise mathematical duality in 1997. A gravity theory in a volume of space is exactly equivalent to a quantum field theory, with no gravity living on that volume's boundary. The two descriptions are not approximations of each other. They are exactly the same physics, written in different languages. This raises a genuinely startling question about dark energy. If the universe has a cosmic boundary, a holographic screen, in the technical language, and if the total amount of information that can be encoded on that boundary is finite, then that information limit might control the energy density of the universe's interior. Holographic dark energy models take this seriously. They propose that the dark energy density in our universe is linked to the size of the cosmic horizon, the boundary beyond which information can no longer reach us because space is expanding too fast. As the universe grows, the horizon's area grows, the maximum allowed information grows, and that growing information boundary sets the energy density of the dark energy filling the interior. The intriguing feature of this proposal is that it connects dark energy to a deep principle about information in the universe, rather than to a specific particle or field. The acceleration of the universe, in this view, is the universe organizing itself up to the limits of what its own boundary can encode. Holographic dark energy models make specific predictions about how the dark energy density should evolve over cosmic time, and several versions have been tested against observational data. Some fit the data reasonably well. Others have already been ruled out. The field is active and contested. But the holographic idea has triggered something deeper. If gravity itself is an emergent phenomenon, something that arises from the thermodynamics of information on surfaces, then dark energy might not be a substance at all. It might be a consequence of how space-time encodes and processes information at the largest possible scales. This idea was developed into a complete framework by theoretical physicist Eric Verlinde, starting around 2010. He proposed that gravity is an entropic force, not a fundamental one, and his framework has direct implications for dark energy that look surprisingly like what we observe. Understanding Verlinde's idea requires stepping back from particles and fields entirely, and thinking about what gravity actually is at the deepest level we currently understand. Eric Verlinde's proposal starts from a simple observation: gravity behaves like thermodynamics. Thermodynamics describes how heat flows, how entropy increases, how macroscopic properties like temperature and pressure emerge from the collective behavior of enormous numbers of microscopic particles. You never need to track individual molecules to describe how a gas expands. The large-scale behavior emerges from statistics. Verlinde noticed that the equations governing gravity look structurally similar to the equations governing thermodynamics. Jacob Bekenstein and Stephen Hawking had already shown that black holes have temperature and entropy, deeply thermodynamic properties for what should be a purely gravitational object. Physicist Ted Jacobson showed in 1995 that Einstein's field equations can be derived from thermodynamic reasoning applied to small regions of spacetime. Gravity, in this picture, is what thermodynamics looks like when applied to the information encoded in space. Verlinde took this further. He proposed that dark energy is the consequence of the quantum information stored in space itself, specifically in the vast volume of space that has no matter in it. In ordinary regions of space, near galaxies and stars, the quantum information in the vacuum organizes itself around matter. But in the enormous empty voids between galaxy filaments, the information takes its ground state, and the response of matter to the thermodynamics of that information field looks, from the outside, like a large-scale repulsion, like dark energy. In Verlinde's framework, dark energy isn't a substance. It's a mismatch between how information wants to organize itself and how matter distributes itself across space. The repulsion you measure when you track galaxies drifting apart isn't a force being applied. It's a geometric and informational consequence of the quantum structure of space-time itself. This sounds abstract, but Verlinde's framework makes concrete predictions. In galaxies with very little ordinary matter, dwarf galaxies which have enormous dark matter halos relative to their visible stars, the entropic correction to gravity produces effects that look precisely like dark matter. Verlinde argues his framework could simultaneously explain dark energy and dark matter as two faces of the same underlying information physics. The The proposal is controversial. Some theorists find it compelling and have developed it further. Others argue that it lacks the mathematical precision needed to constitute a complete theory. Direct tests are difficult because the predictions overlap significantly with standard models in most regimes. The differences show up at the edges, in the outskirts of galaxies, in the voids, in subtle correlations between galaxy structures and the large-scale distribution of matter. What makes Verlinde's idea significant, beyond its specific predictions, is the conceptual shift it demands. If gravity and dark energy are both emergent from quantum information, then neither is fundamental. The search for dark energy's ingredients in a new particle or field would be looking in the wrong place entirely. The ingredient would be information itself. And once you start thinking about information as a physical substance, the questions get stranger. What happens when the universe undergoes a transition? Not in temperature, but in the structure of the information encoded in its vacuum, because space-time may have already survived one such transition. And if it survived one, there's no reason to assume it can't happen again. Water freezes, steam condenses, iron magnetizes below a certain temperature. These are phase transitions, moments when a system reorganizes itself into a completely different state because a lower energy configuration becomes available. Physicists believe the universe has undergone phase transitions before. In the earliest moments after the Big Bang, when temperatures were unimaginably high, the fundamental forces of nature were unified into a single force. As the universe cooled, symmetries broke. The unified force separated into the strong nuclear force, the weak nuclear force, and electromagnetism. Each breaking was a phase transition, a moment when the quantum fields filling space snapped into a new configuration. The Higgs field, confirmed experimentally in 2012, is a direct consequence of one such transition. Before that transition, the quarks and electrons of the early universe were massless, moving at the speed of light. When the universe cooled to a critical temperature, the Higgs field settled into a non-zero value throughout all of space. After that moment, particles interacting with the Higgs field gained mass. The transition changed the laws of physics as experienced by every particle in existence. Now the unsettling question. The Higgs field settled into its current value because that value is a local minimum, a stable resting state, like a ball sitting in a valley. But calculations suggest it may actually be a false minimum. A deeper valley might exist. If the Higgs field were to tunnel quantum mechanically into that lower state, it would trigger a phase transition spreading outward at the speed of light, converting space into a new vacuum with different physical constants. Nothing inside that expanding bubble would survive. The laws of physics inside would be different from the laws outside. Matter, as we know it, would cease to exist. This scenario is called vacuum decay. Measurements of the Higgs boson's mass suggest we live tantalizingly close to the boundary between a stable and metastable vacuum. Whether we sit safely inside stability or precariously on the edge is not yet settled. Now connect this to dark energy. If dark energy is the energy of the vacuum, the value of the quantum fields in their current ground state, then a phase transition would change dark energy completely. The new vacuum state would have a different vacuum energy. If that energy is higher than the current value, the transition generates an explosion of energy as the new vacuum expands. If lower, the new vacuum is more stable, and dark energy in the new regions drops to an even smaller value. Some models of dark energy actually require a future phase transition. In false vacuum scenarios, the universe sits at a metastable dark energy value today, and at some future moment, perhaps triggered by quantum fluctuations, the field will tunnel to a true minimum. The transition propagates, dark energy changes, and the geometry of space reorganizes. We have no way of knowing when this happens or whether the trigger has already occurred somewhere in our unobservable cosmos. The transition bubble, expanding at the speed of light, would be invisible until it arrived. We'd have no warning. Physicists take this seriously because the math supports it. The Higgs field metastability is calculated from measured physical constants. The result is probably stable, possibly not, and it raises a question that cuts across every theory of dark energy. If the vacuum can transition, then the dark energy we measure today might be temporary, not the ground state of the universe, but a rest stop on the way to something else. What that something else is depends on which theory you ask. Every dark energy model we've covered accepts the same premise. General relativity describes gravity correctly, and something extra must exist to explain cosmic acceleration. Modified gravity theories take a different road. They propose that general relativity is an approximation, extraordinarily accurate at solar system scales, but wrong at the scale of galaxy clusters and beyond. In that picture, what we call dark energy is actually gravity misbehaving at large distances. This idea has precedent. Newtonian gravity worked perfectly for centuries. Then, precise measurements of Mercury's orbit revealed a tiny discrepancy that Newtonian mechanics couldn't explain. Einstein's general relativity corrected it. The lesson of that episode: a theory can work across an enormous range of scales and still break down at the edges. The most studied class of modified gravity theories replaces Einstein's equations with a generalized version where the term describing spacetime curvature is replaced by a function of that curvature. At small curvatures, cosmological scales, the enormous voids between galaxy filaments, the function deviates from the standard prediction. At high curvatures, near stars near black holes, it reduces back to standard general relativity. The theory passes all the precision tests in our solar system, and then diverges at cosmic scales in a way that mimics dark energy. The observational challenge is separating these predictions from those of standard dark energy models. Both predict an accelerating universe. Both produce similar large-scale structures. The differences show up in the detailed patterns of how matter clusters, in the growth rate of cosmic structures over time, and in how gravitational lensing, the bending of light by mass, behaves across different scales. Some modified gravity theories predict that the growth rate of cosmic structures should be slightly different from what a cosmological constant predicts. Upcoming galaxy surveys will measure this growth rate with enough precision to distinguish between the two scenarios. This is a genuine test, not a philosophical debate. There are also more radical proposals. One theory called tensor vector scalar gravity was designed primarily to explain galaxy rotation curves without dark matter, but it also modifies gravity at large scales in ways that could explain cosmic acceleration. Another framework proposes that gravity leaks into extra dimensions at large distances. The force weakens faster than inverse square law at enormous scales, mimicking a repulsive effect on the expansion. These theories face serious challenges. Many have been constrained significantly by the 2017 detection of gravitational waves from a neutron star merger, observed simultaneously with gamma rays. The fact that gravitational waves travel at exactly the speed of light, to extraordinary precision, rules out many modified gravity theories that predict a different speed for gravitational waves. After that, the landscape of viable modified gravity theories shrank dramatically. The survivors are fewer and more specific, constrained, not eliminated. And here's where the current state of the field becomes genuinely suspenseful. There is now a measurement, made with two completely independent methods, that doesn't agree. The expansion rate of the universe, measured two different ways, gives two different answers. And that disagreement might be pointing directly at new physics. Physics that no current theory, including standard dark energy, fully explains. The universe has one expansion rate. Physicists call it the Hubble constant. It describes how fast galaxies recede per unit of distance. Every galaxy survey, every cosmic map, every model of the universe's history depends on knowing this number accurately. Two teams of scientists measured it. They used completely different methods across different cosmic epochs. With different instruments, they got different answers. And the gap between those answers has been growing larger, not smaller, as measurements improve. The first method uses the cosmic microwave background, the faint afterglow of radiation from 380,000 years after the Big Bang. By analyzing the patterns of temperature variation in this radiation, the Planck satellite team calculated the Hubble constant with exquisite precision. Their answer, approximately 67 kilometers per second per megaparsec. Every megaparsec of distance, roughly 3 million light years, adds 67 kilometers per second of recession speed. The second method builds a cosmic distance ladder. First, Astronomers measure distances to nearby Cepheid variable stars using the pulsation brightness relationship Hubble used a century ago. Then they calibrate distances to a specific type of exploding star, type Ia supernovae, using nearby examples anchored by the Cepheid measurements. Then they use the supernovae to measure galaxy recession speeds across billions of light years. The answer from this method: approximately 73 kilometers per second per megaparsec. 67 versus 73, a difference of about 9%. In a field where measurements aim for precision below 1%, this is enormous. The statistical confidence that this disagreement is real, not noise or random error, exceeds 5 sigma. In physics, 5 sigma is the threshold for claiming a discovery. The Hubble tension is, by the standards of the field, a confirmed discrepancy. Both methods have been cross-checked, repeated, and scrutinized for systematic errors. The Planck team has rechecked their analysis multiple times. The Distance Ladder team, led by astronomer Adam Rees, who shared the Nobel Prize for the original discovery of cosmic acceleration, has independently verified their calibrations using entirely different tools, including observations from the James Webb Space Telescope. The tension persists. What could cause it? Several possibilities exist, each with different implications for dark energy. If the early universe had a brief burst of extra dark energy, sometimes called early dark energy, before recombination, it would shift the apparent Hubble constant derived from the cosmic microwave background upward. If dark energy's equation of state varies with time, it could introduce a systematic error into one measurement chain. If dark matter has properties slightly different from the standard model, it could bias the cosmic microwave background analysis. And then there's the most dramatic possibility. Our standard model of cosmology is simply missing something. Some ingredient, some interaction, some physics we haven't thought of yet. The Hubble tension has energized cosmology in a way that hasn't been seen since the original discovery of dark energy. Hundreds of theoretical papers propose solutions. Observational teams are designing new experiments specifically to resolve it. The answer matters because it points directly at the nature of dark energy. And in 2024, a massive new galaxy survey released data that made the tension even more urgent and suggested something about dark energy that nobody expected. In April 2004, the Dark Energy Spectroscopic Instrument Collaboration released results from its first year of observations. The instrument, mounted on a telescope in Arizona, had measured the positions and recession speeds of roughly 6 million galaxies and quasars, mapping the three-dimensional structure of the universe across 11 billion years of cosmic history. The goal was to use a feature called baryon acoustic oscillations as a standard ruler. In the early universe, sound waves traveled through the hot plasma of matter and radiation, compressing and expanding it rhythmically. When the universe cooled enough for electrons and protons to combine into neutral atoms, the sound waves froze. They left a preferred clustering scale imprinted in the distribution of matter, a characteristic separation between galaxy clusters, roughly 500 million light-years across, that appears consistently throughout the cosmic web. By measuring this scale at different cosmic epochs, different redshifts, corresponding to different times in cosmic history, astronomers can track how the expansion rate has changed over time, and from that, infer the properties of dark energy driving the acceleration. When the DESI team analyzed their data, they found a preference for dark energy that evolves over time. Specifically, the data fit better with models where dark energy was stronger in the past and has been weakening as the universe ages. The equation of state showed signs of being above the cosmological constant value at earlier times and drifting below it more recently. This is a 2 sigma hint, not a 5 sigma confirmation. At 2 sigma, the result has roughly a 1 in 20 chance of being statistical noise. Physicists don't call this a discovery. They call it a tension, and they pay very close attention to it. If confirmed with more data, and DESI is designed to gather roughly 5 times more by its survey's completion, the implications are seismic. A cosmological constant cannot change over time by definition. If dark energy varies, the simplest and most elegant explanation for dark energy is ruled out. Every model in contention would be a dynamic one: quintessence, holographic dark energy, modified gravity, or something entirely new. The DESI result also interacts with the Hubble tension in interesting ways. Some of the models that best explain the evolving dark energy hint also reduce the Hubble tension compared to a static cosmological constant. Two independent problems might have a single solution, which is precisely the kind of convergence physicists find most compelling. A weakening dark energy also changes the long-term fate of the universe. If the repulsive pressure is declining rather than holding steady, the acceleration of expansion may slow down in the far future. Given enough time, gravity could reassert itself. Instead of the universe expanding forever toward heat death, a declining dark energy opens the possibility of eventual collapse, a big crunch replacing the long cold fade. But before the universe's fate can be decided by better data, physicists have to grapple with something even more philosophically challenging, a framework that might explain why dark energy has the value it does. And the answer involves an almost incomprehensible landscape of possibilities. String theory proposes that the fundamental ingredients of nature are not point particles, but tiny, vibrating strings of energy. Different vibration modes correspond to different particles. The theory requires extra dimensions beyond the 4 we experience, up to 10 or 11 total, and those extra dimensions are curled up at scales too small to detect. Here's the critical detail. Those extra dimensions can curl up in an astronomically large number of different ways. Each different configuration, each different shape of the compactified extra dimensions produces a different vacuum state with different effective laws of physics, a different mass for the electron, a different strength of gravity, and a different value for the cosmological constant. The number of distinct configurations is staggering. Current estimates suggest it's somewhere around 10 to the power of 500. That's a number so large that writing it out would require more digits than there are atoms in the observable universe. Each configuration is a possible vacuum. Each vacuum is, in principle, a possible universe with its own physical constants. This collection of possible vacua is called the string theory landscape. In a landscape with 10 to the 500 possible cosmological constant values, some of those values will be small and positive, close to what we measure. The question stops being, why is the cosmological constant so small? And becomes, why do we find ourselves in one of the vacua where it's small? The proposed answer is selection. In vacua where the cosmological constant is large and positive, space expands too fast for matter to clump. Gravity never wins locally. Stars and galaxies never form. Complexity never develops. Life never emerges to ask questions. In vacua where the cosmological constant is large and negative, the universe collapses before structures form. The tiny window of cosmological constant values, compatible with the existence of galaxies, stars, planets, and observers, is narrow. We live in one of those because those are the only ones where anyone can live. This argument is called the anthropic principle when applied to physical constants. Among physicists, opinions about it are deeply divided. Some find it compelling. The landscape exists in the math of string theory. The selection effect is real. The observed value of the cosmological constant sits comfortably within the anthropically allowed window. The prediction matches observation. Case closed. Others find it deeply troubling. A theory that can accommodate any value of a constant by invoking observer selection isn't making a prediction. It's absorbing any possible result. If every vacuum is equally real somewhere in the landscape, and we simply live in one where conditions allow our existence, then the cosmological constant problem hasn't been solved. It's been dissolved. The question of why our universe has this specific cosmological constant gets the answer. Because universes that don't are uninhabited. That answer satisfies the logic, but it's a very different kind of physics than anything that came before. The landscape also implies something vast and vertiginous. If all those vacua are physically real, they must be realized somewhere. Eternal inflation, a theory of rapid early expansion, naturally produces a multiverse where different regions of space settle into different vacua. Our observable universe would be one bubble among an incomprehensibly large number of others, each with its own physics. For some researchers, this is the most honest answer physics can currently give. For others, a theory that cannot make predictions beyond "we exist" has stepped outside the boundaries of science. What's certain is that the landscape raised a challenge that forced physicists to ask harder questions. And the hardest question of all may be whether the dark energy we measure is connected to something even more fundamental: the nature of time itself. Most theories treat dark energy as a thing in space, a field, a constant, an energy density filling the vacuum. But a smaller set of theorists have asked whether dark energy might be better understood as a property of time, specifically as a consequence of the thermodynamic arrow of time that gives the universe a direction from past to future. The second law of thermodynamics says that in a closed system, entropy, disorder, always increases or stays the same. This gives time its arrow. The past has lower entropy than the future. We remember the past and not the future, because records encode information about lower entropy states, and the universe always moves toward higher entropy. But here's the cosmological puzzle. Why did the universe start with such extraordinarily low entropy? The Big Bang produced a remarkably ordered initial state. All that order has been unwinding ever since, and the unwinding is what we experience as the forward direction of time. Physicist Sean Carroll and collaborators have proposed that the initial low-entropy state of the universe is connected to the emergence of time's arrow, and that dark energy plays a specific role in this story. A universe with a small positive cosmological constant has a maximum entropy state, a de Sitter spacetime, named after the Dutch mathematician Willem de Sitter, where everything has expanded apart and thermal equilibrium is reached. Dark energy determines what that maximum entropy state looks like. The entire history of the universe, stars, galaxies, life, complexity, is the trajectory from a low entropy beginning toward that de Sitter equilibrium. In this picture, dark energy isn't an ingredient added to the universe. It defines the destination, the end point, the thermal death that the universe is slowly approaching as it expands. Some researchers have gone further, proposing that time itself might be emergent, that the experience of moments passing, of causality, of before and after, arises from quantum entanglement between different subsystems of the universe. In these frameworks, what we perceive as the universe's evolution through time is actually the universe exploring its quantum state space. The expansion of the universe and the dark energy driving it might be signatures of how quantum information reorganizes as the universe samples its possible configurations. These proposals are at the frontier, more speculative than modified gravity or quintessence, less developed mathematically, harder to test, but they point towards something worth sitting with. The expansion of the universe might be deeply connected to why time has a direction at all. Dark energy might be less like a substance and more like a structural feature of how reality is organized at the deepest level. And that possibility, that dark energy and the arrow of time are aspects of the same underlying physics, opens the door to the most ambitious approaches of all. Approaches that try to describe gravity and time and space as emerging together from something more fundamental than any of them. Those approaches live at the intersection of quantum mechanics and general relativity. And what they suggest about dark energy is strange in ways that earlier chapters only hinted at. General relativity breaks down at the Big Bang. The equations produce a singularity, a point of infinite density, infinite temperature, infinite curvature. Physicists treat this as a signal that the theory is incomplete, not a description of reality. To understand what actually happened at the beginning and what drives the universe's expansion today requires a theory that merges quantum mechanics with gravity. Loop quantum gravity is one serious attempt at that merger. Instead of treating space-time as a smooth, continuous fabric, it proposes that space itself is built from discrete chunks, tiny loops of quantum geometry, each with a minimum size on the order of the Planck length, which is roughly 10 to the minus 35 meters. Space, in this framework, has a granular structure at the smallest scales, the way matter is made of atoms rather than being infinitely divisible. When physicists apply loop quantum gravity to cosmology, the field called loop quantum cosmology, the Big Bang singularity disappears. Instead of infinitely dense matter crushed to a point, the equations describe a big bounce. The universe that preceded ours was contracting. As it compressed, quantum geometry effects became significant at Planck scale densities. The compression stopped. A repulsive quantum gravity effect reversed it, launching the expansion we currently inhabit. This bounce has direct implications for dark energy. In loop quantum cosmology, the quantum corrections to the geometry of space-time introduce additional terms in the equations governing expansion. These terms behave differently at different energy densities. In the early universe, they drive the bounce. At low energy densities in today's universe, they produce a small residual effect on expansion that can mimic a cosmological constant. Some models within loop quantum cosmology predict a dark energy value that emerges naturally from the quantum geometry of spacetime, without requiring a separate field or a fine-tuned constant. The repulsion driving cosmic acceleration would be a direct consequence of the discrete structure of space at the Planck scale, projected up to cosmological scales through the dynamics of the expanding universe. The prediction isn't precise enough yet to confirm or rule out from current observations. The theory has genuine mathematical challenges. Connecting the Planck scale quantum geometry to the smooth spacetime of everyday physics requires approximations whose accuracy is still being established. But the framework is internally consistent, produces a bounce cosmology that avoids the initial singularity, and offers a path to explaining dark energy from quantum gravitational geometry rather than an added ingredient. There's something conceptually striking about this approach. If it's right, dark energy doesn't come from a new substance or a mysterious field. It comes from the fact that space itself has a minimum size. The granularity of space-time at the tiniest scales leaves a fingerprint on the largest scales. The universe accelerates because space cannot be compressed beyond a limit, and the memory of that limit echoes through billions of years of expansion. Whether that echo is exactly what we measure as dark energy remains open. The math is developing, the observational tests are being designed, and a completely separate line of quantum gravity research has arrived at a different but equally radical idea, one that dissolves the boundary between gravity, entropy, and the structure of space-time in a way that reframes what dark energy could possibly mean. In 2013, physicist Mark van Ramsdonk published a paper with an idea so striking it circulated far beyond theoretical physics. He argued that the geometry of space-time, its shape, its connectivity, the fact that distant regions are connected at all, is built from quantum entanglement. Entanglement is the quantum phenomenon where two particles share a correlated state regardless of the distance between them. Measure one particle, and you instantly know something about the other, no matter how far apart they are. Einstein called it spooky action at a distance, and spent years trying to prove it couldn't be fundamental. Experiments proved it is. Van Ramsdonk's insight was this: in the holographic framework, where a volume of space is equivalent to quantum field theory on its boundary, the geometry of the interior space is determined by the entanglement structure of the boundary theory. Two regions of the boundary that are highly entangled correspond to two regions of the interior that are close together, connected by short geometric paths. Two regions of the boundary with low entanglement correspond to interior regions that are far apart, or even disconnected. In a famous thought experiment, he imagined taking a boundary quantum system in an entangled state and gradually reducing the entanglement between its two halves. As the entanglement decreases, the interior geometry responds. The two corresponding regions of the interior spacetime move farther apart. Reduce the entanglement to zero, and the interior spacetime splits into two disconnected pieces. Entanglement stitches the fabric of space together. This idea has been formalized through the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. It states that two entangled particles are connected by a microscopic wormhole, a shortcut through spacetime called an Einstein-Rosen bridge. Entanglement and geometric connectivity are two descriptions of the same physical relationship. The implication for dark energy is profound and still being worked out. If spacetime geometry emerges from entanglement, then the expansion of the universe changes the entanglement structure of the universe's quantum state. As space grows, the entanglement between different regions evolves. The dark energy driving that expansion would be, in this picture, the energy cost of changing the entanglement structure of spacetime itself. Expansion requires reorganizing quantum information. That reorganization has an energy associated with it. That energy is what we observe as dark energy. This is speculative. The technical machinery connecting entanglement dynamics to observed dark energy values is not yet complete, but the conceptual trajectory is clear. The most fundamental theories of quantum gravity suggest dark energy might be the energy of weaving space-time together from quantum correlations. If that's right, dark energy isn't in space. Dark energy is partly responsible for space existing at all, and that changes the question entirely. Instead of asking what particle or field dark energy is made of, the question becomes, what determines the entanglement structure of the universe's quantum state? And can that structure change? We've touched on the vacuum catastrophe before. Now it's time to face it directly, with everything we've built up. Quantum field theory requires that every quantum field has a ground state energy, a zero-point energy that cannot be removed. For a single field, this energy is infinite, which immediately signals that something needs to be controlled mathematically. Physicists use a technique called renormalization to handle this. They set a cutoff scale, the maximum energy at which the theory is trusted, and calculate the vacuum energy up to that scale. The most natural cutoff is the Planck scale, the energy at which quantum gravity effects become important and the current theory breaks down. Below the Planck scale, quantum field theory is expected to apply. Calculating the vacuum energy with this cutoff gives a number, the Planck energy density, roughly 10 to the 96 kilograms per cubic meter. The observed dark energy density, the tiny repulsive pressure driving cosmic acceleration, is measured at roughly 10 to the minus 27 kilograms per cubic meter. Divide the prediction by the observation. The ratio is 10 to the 123. Written as a fraction, the numerator has a 1 followed by 123 zeros above a single 1 below. Every other prediction in quantum field theory agrees with experiment to extraordinary precision. The magnetic moment of the electron is predicted and measured to agree within 1 part in a trillion. Quantum electrodynamics routinely produces predictions accurate to 10 decimal places. The standard model of particle physics, tested across decades at accelerators worldwide, has never been seriously contradicted. And then this, the same theoretical framework, applied to the vacuum, produces a number 123 orders of magnitude off. Something cancels the vacuum energy down. Supersymmetry, if it exists, would pair every boson with a fermion, and their vacuum energy contributions would partially cancel. But supersymmetry, even if perfect, only cancels contributions down to the supersymmetry breaking scale. The residual is still many orders of magnitude larger than what's observed. The cancellation helps, but doesn't solve the problem. What's needed is a cancellation of extraordinary precision. The contributions from all quantum fields, electrons, quarks, photons, gluons, Higgs bosons, and everything predicted, but not yet discovered, must add and subtract to leave a residue of 1 part in 10 to the 123. Getting that cancellation requires that the positive and negative contributions match to 123 decimal places, with no mechanism requiring it. Some physicists argue this can only be explained by a symmetry we haven't found yet, a new symmetry that forces the vacuum energy to zero exactly, and then some other mechanism adds back the tiny observed value. Proposals exist, but none have succeeded. Others argue the anthropic landscape is the only viable explanation. With 10 to the 500 possible vacuum states, some will land in the anthropopically allowed range by chance, and those are the ones that produce observers. The number isn't fine-tuned, it's selected. And a third group suspects the answer requires abandoning the Planck scale cutoff entirely. If quantum gravity removes the concept of infinitely short distances, as loop quantum gravity suggests, then the calculation changes at its foundation. The enormous prediction may be an artifact of applying quantum field theory beyond its domain of validity. Each resolution demands different physics, and none of them can yet be tested directly. The catastrophe stands as the sharpest open wound in theoretical physics. But the wound has a shape, and that shape has started to point toward places we haven't looked before. Symmetry is the organizing principle of modern physics. Every fundamental force corresponds to a symmetry. Electromagnetism arises from a symmetry of the quantum phase of charged particles. The weak nuclear force arises from a symmetry between electron-type and neutrino-type particles. The strong force arises from a color symmetry of quarks. General relativity arises from the symmetry of space-time under arbitrary coordinate changes. When a symmetry breaks, when the equations have it but the physical state doesn't, the consequences are dramatic. The Higgs mechanism is a broken symmetry. The universe at high temperatures respected an electroweak symmetry combining electromagnetism and the weak force. Below a critical temperature, that symmetry broke. The Higgs field settled into a non-zero value. Particles gained mass. The two forces separated into distinct interactions with different strengths and ranges. The cosmological constant problem has led many physicists to suspect a similar story. At some energy scale, there may exist a symmetry that forces the vacuum energy to exactly zero. The symmetry is exact at high temperatures. As the universe cools through some critical point, the symmetry breaks. The vacuum energy, no longer protected, acquires a value. And if the symmetry breaking is gentle enough, if the breaking is small, the residual vacuum energy is tiny. The most discussed candidate for this protective symmetry is supersymmetry. In a perfectly supersymmetric universe, every force-carrying boson has a partner matter particle, a fermion, with exactly the same mass and opposite vacuum energy contribution. The bosons contribute positive vacuum energy, the fermions contribute negative, and they cancel perfectly. Vacuum energy is exactly zero by symmetry. The universe we observe is clearly not perfectly supersymmetric. The partner particles have very different masses from the known particles, if they exist at all. So supersymmetry, if real, is broken. The breaking gives the partner particles high masses, pushes them beyond our current detection range, and leaves a residual vacuum energy whose size depends on how supersymmetry breaks. The residual from supersymmetry breaking is vastly smaller than the Planck scale prediction, but it's still many orders of magnitude larger than the measured dark energy. Supersymmetry alone doesn't close the gap. What might close it is a second symmetry operating on top of the first. Some theorists propose that a conformal symmetry, a symmetry of scale where the physics looks the same at all distance scales, might further suppress the vacuum energy. Others propose that a discrete symmetry relating different vacuum energy contributions forces additional cancellations. Some models invoke both. Each proposal is constrained by observations. If the symmetry breaking has observable consequences, new particles, new forces, deviations from known behavior at high energies, experiments can test it. The Large Hadron Collider has searched extensively for supersymmetric particles and found none in the expected mass ranges. The absence tightens the constraints. A symmetry explanation for the vacuum energy would be immensely satisfying. It would say, the dark energy we observe is the small residue of a broken protection mechanism, the way a river is the residue of a broken dam. The value would have a calculable cause rather than an anthropic selection. Whether that symmetry exists, and what it is, remains one of the deepest open questions in physics, and searching for it has pushed physicists toward an unexpected frontier. The properties of dark energy are now directly tied to what happens at the very highest energies, near the Planck scale. To understand the very largest thing we observe, we may need to understand physics at the very smallest scale imaginable. The Planck length is roughly 10 to the minus 35 meters. The Planck energy is the energy concentrated in that length. Both represent the frontier where quantum mechanics and gravity meet, where our current theories break down and something new must take over. We have no confirmed physics beyond the Planck scale. Here's the problem. When physicists model inflation, the rapid expansion of the very early universe, the quantum fluctuations that seeded all cosmic structure started smaller than the Planck length before inflation stretched them to astronomical sizes. These fluctuations crossed what physicists call the trans-Planckian boundary, moving from sub-Planckian to observable scales. The predictions of inflation match the observed structure of the universe extraordinarily well, which means either the trans-Planckian physics happens to leave the predictions unchanged, or we're getting lucky. Dark energy faces a version of the same problem. In quintessence models, the slow-rolling field must be incredibly light, lighter than any known particle, and must roll with extreme precision over billions of years. The field's behavior is sensitive to quantum corrections from all the heavier physics above it in the energy hierarchy. Every heavy particle that interacts with the quintessence field even weakly, contributes quantum corrections to the field's mass. Keeping the field light against these corrections requires either a fine-tuning or a protective symmetry. Some theorists have proposed that the quintessence field has a shift symmetry, a symmetry that allows the field's value to change without changing the physics. This protects the field's mass from quantum corrections in the same way that the symmetry protecting the photon's masslessness works in electromagnetism. Fields protected by shift symmetries are called axions when the symmetry is related to a phase, and pseudo-Nambu-Goldstone bosons in the general case. Several dark energy proposals are built on these structures. The axion-like quintessence field would have a natural lightness protected by symmetry. Its potential energy would have a specific shape determined by how the symmetry is slightly broken. The rolling of the field would be tied to the symmetry breaking scale, which could naturally be set to the observed dark energy scale, without fine-tuning. These models are testable in principle. The field couples weakly to photons, which means it can rotate the polarization of light from distant galaxies, a phenomenon called cosmic birefringence. Several observational groups have reported hints of this rotation in the cosmic microwave background polarization data. The hints are at the 2 sigma level, suggestive, requiring confirmation, consistent with an axion-like dark energy field, but not yet established. If cosmic birefringence is confirmed at high significance, it would provide direct evidence that dark energy is a dynamical field with specific symmetry properties. The confirmation would rule out the pure cosmological constant, support axion-like quintessence, and point toward the symmetry-breaking scale responsible for dark energy. The measurement requires extraordinary precision and careful control of instrumental effects. Several upcoming experiments are designed to improve it significantly. And here, the physics of the very small and the very large converge in a genuinely uncomfortable way. The same axion-like fields proposed to explain dark energy are also candidates for dark matter in certain mass ranges, and are predicted by string theory in the context of the landscape. If any of these connections are real, dark energy, dark matter, and the string theory landscape are not separate problems. They're aspects of a single underlying structure we haven't yet seen clearly. Black holes are the universe's most extreme concentrations of gravity. Their event horizons are boundaries beyond which nothing escapes. They grow by swallowing matter, shrink imperceptibly through Hawking radiation, over incomprehensible timescales, and seem permanent on any human scale of time. Dark energy complicates this picture in 2 ways. The first is direct and mechanical. As dark energy drives the expansion of the universe, it creates a competing boundary around every observer, called the cosmic event horizon. Beyond this horizon, space recedes faster than light, and no signal can ever reach us from there. We have a boundary around us defined by expansion, and black holes have a boundary around them defined by gravity. The universe now contains 2 kinds of event horizons, and they have a remarkable thermodynamic parallel. Hawking showed that black hole event horizons have a temperature and emit radiation. Physicists Gibbons and Hawking showed in 1977 that the cosmic event horizon in a dark energy universe also has a temperature and emits radiation, called de Sitter radiation. The universe in its far future, dominated by dark energy and emptied of matter by expansion, settles into a de Sitter state with a tiny but non-zero temperature throughout all of space. This has consequences for the long-term fate of everything. Ordinary matter in a de Sitter universe slowly exchanges energy with the ambient de Sitter radiation over unimaginably long timescales, far longer than the current age of the universe. Even black holes radiate away through Hawking radiation and disappear. After they're gone, only the de Sitter temperature remains. The universe reaches maximum entropy. Nothing organized can exist. This is the heat death of the universe, and dark energy is what drives the cosmos into this final state. The second complication is more speculative. In phantom energy models, where dark energy density grows over time, black holes face a different fate. The growing phantom energy eventually overwhelms even the gravity holding a black hole together. Black holes evaporate, not through Hawking radiation, but through the phantom energy tearing at their event horizons. The expansion of space eventually penetrates even the interior of a black hole, dissolving the singularity from the outside in. This happens before the Big Rip reaches atomic scales. A black hole being dissolved by phantom energy is a striking image, the most gravitationally extreme object in the universe, undone by the energy of empty space. There's a deeper connection here that physicists are still exploring. The thermodynamics of event horizons, black hole horizons, cosmic horizons, and dark energy are connected through the holographic principle. The entropy of a region of space is bounded by the area of its boundary in Planck units. Dark energy determines the size of the cosmic horizon. The cosmic horizon's area determines the maximum entropy of the observable universe. So dark energy determines how much information the universe can ultimately contain. If you change dark energy, if the cosmological constant were larger, the cosmic horizon would be smaller, the maximum entropy would be lower, and the universe would be informationally poorer. A universe with a larger dark energy is a universe with a smaller capacity for complexity. Our universe has exactly the dark energy value that allows for the enormous information content needed for galaxies, stars, chemistry, and biology, and then slowly ends in a heat death whose temperature is set by the same dark energy. Whether that's coincidence, selection, or something deeper is a question the next generation of physicists will inherit. Every detection of dark energy so far has been indirect. We measure its effect on the expansion history of the universe. We infer its presence from the acceleration of galaxy recession. We calculate its energy density from the geometry of the cosmic microwave background. We've never caught a dark energy particle in a detector. We've never produced dark energy in an accelerator. We've never isolated it in a lab. The question of whether direct detection is possible depends entirely on what dark energy is. If it's a pure cosmological constant, a fixed property of space-time with no associated particle, then direct detection is impossible, in principle. There's nothing to catch. The repulsion is built into the geometry of empty space. You can't put geometry in a particle detector. If dark energy is a dynamical field, quintessence and axion-like scalar, or something similar, then the field has an associated particle, and that particle can in principle interact with matter. The challenge is that any interaction must be extraordinarily weak. If the quintessence field interacted strongly with matter, we'd have measured deviations from standard gravity already. The fifth force, produced by a strongly coupled quintessence field, would show up in precision tests of the equivalence principle, experiments checking whether all objects fall at the same rate, regardless of composition. Such tests have been done with extraordinary precision, using torsion balances, atom interferometers, and lunar laser ranging. No deviation has been found. The quintessence coupling to matter is constrained to be tiny, but tiny is measurable in principle with the right instrument. Several experiments are actively searching. The Microscope satellite mission tested the equivalence principle in orbit with unprecedented precision, setting stringent limits on any fifth force from a dark energy field. Future missions plan improvements of another order of magnitude. Space-based experiments eliminate the vibration noise that limits ground-based tests. The cosmic birefringence signal, the rotation of photon polarization by an axion-like dark energy field, is being pursued by cosmic microwave background experiments, including the Simons Observatory and the planned CMB S4 experiment. These will map the polarization of the microwave background across the full sky with sensitivity orders of magnitude beyond current measurements. The Dark Energy Spectroscopic Instrument is continuing to gather data on the expansion history across cosmic time. The Euclid satellite, launched in 2023, is mapping the three-dimensional structure of hundreds of millions of galaxies to constrain how dark energy affects structure growth. The Vera Rubin Observatory, now operational, is conducting a decade-long survey that will measure weak gravitational lensing, the subtle distortion of distant galaxy shapes by intervening matter, to map the distribution of dark energy and matter simultaneously. These are indirect methods, but they probe different aspects of dark energy's behavior with enough combined precision to distinguish between models that agree on the acceleration but disagree on everything else. Direct detection remains the holy grail. If a fifth force associated with the dark energy field were found, even a tiny violation of the equivalence principle, it would immediately tell physicists that dark energy is a dynamical field give them its coupling strength and point towards its mass and symmetry properties. One clean positive signal would rewrite the field overnight. None has appeared yet. The searches continue. And meanwhile, a theoretical framework has been developed that may tell us what to search for based on deep consistency requirements of the theory itself. In string theory, the landscape contains an enormous number of possible vacuum states, but not every conceivable vacuum is part of the landscape. There is a larger space of seemingly consistent quantum field theories that turn out, on careful examination, to be inconsistent with quantum gravity. Physicists call this region the swampland. Theories that look fine on their own but cannot be embedded in any theory of quantum gravity. Over the past decade, theorists have developed a set of conjectures about what distinguishes the landscape from the swampland. These are called swampland conjectures, and one of them has direct and dramatic implications for dark energy. The de Sitter conjecture proposes that stable de Sitter space, a universe with a positive cosmological constant that is truly static and eternal, might not exist in any consistent theory of quantum gravity. Every attempt to construct a stable positive vacuum in string theory has run into subtle instabilities. The conjecture generalizes this difficulty. All positive vacuum states are either unstable or roll towards zero. If the de Sitter conjecture is correct, a pure cosmological constant, an eternally fixed dark energy value, is forbidden. Dark energy must be dynamical, it must be rolling, and it must satisfy a specific mathematical condition. The rate at which the dark energy field rolls must exceed a certain minimum value relative to the field's energy. The condition is tight enough to conflict with the simplest quintessence models. Those models generally have fields rolling too slowly to satisfy the swampland bounds. Satisfying the conjecture, while also matching the observed acceleration, requires careful model building or a modified version of quintessence. The conjecture also makes a prediction with observational consequences. If dark energy is rolling, the equation of state deviates from the cosmological constant value. The deviation should be large enough to be measurable with current and upcoming experiments. If dark energy is truly rolling fast enough to satisfy the swampland conjecture, Deci, Euclid, and Rubin should see it. The swampland conjecture is a conjecture, not a theorem. It hasn't been proven from string theory's first principles. Some string theorists believe stable de Sitter vacua do exist, and the conjecture is simply wrong. The debate is active and sometimes heated, but if it's right, the implications are enormous. It means the dark energy we observe today is temporary. It will roll. The equation of state will change. The acceleration of the universe will eventually end. The final state of the universe would be a big freeze or collapse, not the eternal de Sitter heat death of the cosmological constant picture. And the swampland conjecture is part of a broader program, using the consistency requirements of quantum gravity to constrain what can exist in the low-energy universe we observe. The largest scales of the cosmos and the deepest structure of quantum gravity are not separate domains. They're connected by constraints that flow in both directions. What's consistent at the Planck scale determines what's possible at the cosmic scale. Dark energy sits at the intersection of both. The Hubble tension, the disagreement between two measurements of the expansion rate, has driven theorists to look for physics that could shift the numbers into alignment. One of the most developed proposals is early dark energy, a brief episode of dark energy-like behavior in the universe's distant past that boosted the expansion rate before the formation of the first atoms. In the standard model of cosmology, the universe before recombination, before electrons and protons combined into neutral hydrogen, roughly 380,000 years after the Big Bang, was filled with a tightly coupled plasma of matter and radiation. Sound waves propagated through this plasma, leaving the baryon acoustic oscillation imprint we use to measure the expansion history today. The Hubble constant, inferred from the cosmic microwave background, depends on the size of the sound horizon, the distance a sound wave traveled before recombination froze it. If you add a brief burst of early dark energy just before recombination, the expansion rate at that moment increases. A faster expansion means the universe was physically smaller when recombination occurred. A smaller universe means a smaller sound horizon. A smaller sound horizon scaled to today's universe implies a higher Hubble constant. The discrepancy shrinks. The appeal of early dark energy is that it potentially solves two problems at once. It resolves the Hubble tension, and it's motivated by the same type of physics already invoked for the current dark energy. A scalar field that briefly activated in the early universe, dominated the energy budget momentarily, then diluted away as the universe expanded, similar to how radiation and matter densities fell as the universe grew, could leave exactly this imprint. The challenge is that early dark energy doesn't solve the tension perfectly. Current data from the cosmic microwave background constrains how much early dark energy could have existed. When models are tuned to resolve the Hubble tension, they sometimes worsen other measurements, the clustering of matter on large scales, or the amplitude of density fluctuations. The solution to one tension creates a pull on another. Several groups have analyzed whether early dark energy is preferred by the data over the standard model. The conclusion is mixed. It helps with the Hubble tension, but the improvement is modest, and it introduces tensions elsewhere. The evidence for early dark energy is not strong enough to claim detection, and some analyses find no preference for it at all. What's significant about early dark energy, theoretically, is what it implies about the nature of dark energy fields in general. If dark energy can briefly activate in the early universe and then fade, then the dark energy we see today might itself be a late-time activation of a similar mechanism. The universe might have had multiple dark energy episodes at different cosmic epochs, each driven by a field settling into a different stage of its evolution. This opens a genuinely different picture of cosmic history, a universe with multiple scalar fields, each dominating at different times, each leaving signatures in the expansion history that precision surveys can detect. The current dark energy would be the latest in a sequence, not the first and only. Testing this requires mapping the expansion rate and structure growth across the full cosmic history with enough precision to see variations that a single cosmological constant cannot produce. That's exactly what the current generation of surveys is designed to do. And if they find those variations, the next question becomes, what sets the schedule? What determines when each field activates and how long it persists? Dark energy makes up 68% of the total energy of the universe today. Matter makes up about 32%. The ratio is roughly 2 to 1. Go back a billion years. Dark energy was smaller relative to matter. Go back 10 billion years. Matter dominated overwhelmingly. Dark energy was a negligible fraction. Go forward 10 billion years. Dark energy will dominate almost completely. Matter will be diluted to irrelevance, and the universe will be an essentially empty, accelerating void. We live at the precise cosmic moment when dark energy and matter are within a factor of 2 of each other. We didn't arrive early, before dark energy mattered. We didn't arrive late, after matter was already irrelevant. We're here at the transition, the only epoch when both are cosmologically significant simultaneously. This is called the coincidence problem. And for a cosmological constant, it has no dynamical explanation. A cosmological constant has the same energy density today that it had 14 billion years ago, and that it will have 14 billion years from now. Matter density, on the other hand, dilutes as the universe expands. It scales as the inverse cube of the scale factor. In a universe with a cosmological constant, the matter density was once enormously larger than the dark energy density, and in the far future it will be negligible. The two cross over exactly once. We happen to be living at that crossover. The probability of finding ourselves at this crossover, if our location in cosmic time were random, is extremely low. The crossover epoch spans a few billion years out of a cosmic history that extends trillions of years into the future. Something about our existence is apparently selecting for this epoch. The anthropic argument applies here too. Observers require matter to have formed into galaxies, stars, and planets. Before the crossover, structure was forming because matter dominated and gravity could win locally. After the crossover, dark energy accelerates expansion fast enough to prevent new structures from forming. The epoch of structure formation is roughly coincident with the matter-dark energy crossover. We exist during the crossover because that's when the conditions for our existence were possible. This explanation works logically but feels incomplete. It says we shouldn't be surprised to observe the coincidence because we could only exist when the coincidence is occurring. That's true, but it tells us nothing about the mechanism. It doesn't explain why the cosmological constant has the value it does. Only why, given that value, observers find themselves at the crossover. Quintessence offers a partial dynamical resolution through a feature called tracker behavior. In some quintessence models, the field automatically adjusts its energy density to track the dominant energy component of the universe. During radiation domination, the field tracks radiation. During matter domination, it tracks matter. Eventually, the tracking fails and the field's energy overtakes matter, driving acceleration. The crossover happens naturally as part of the field's dynamics, without requiring fine-tuning. Tracker quintessence turns the coincidence from an accident into a consequence. The dark energy density is comparable to matter density today because the field is designed by its own equations of motion to arrive at domination at roughly this time. Whether tracker quintessence, anthropic selection, or something yet unknown is the true explanation, the coincidence problem is a genuine clue. Whatever dark energy is, its value and its timing are intertwined with the existence of structure in the universe. That's either the deepest coincidence in nature, or a window into physics we haven't discovered yet. If string theory's landscape is real, and if eternal inflation populates it, then the universe we inhabit is one bubble among an effectively infinite number of others. Each bubble nucleated from a rapid inflationary expansion into a different vacuum state, with different physical constants, different particle masses, different forces, and a different cosmological constant. In most bubbles, the cosmological constant is large and positive, or large and negative, or zero with exact precision. In bubbles with a large positive cosmological constant, space expands so fast that matter never clusters, no galaxies form. In bubbles with a large negative constant, the universe collapses in a big crunch before any complexity develops. In bubbles with an exactly zero constant, structure forms but expansion eventually halts and recollapse eventually follows, possibly allowing life, possibly not, depending on many other factors. In a small fraction of bubbles, an exponentially tiny fraction of an effectively infinite number, the cosmological constant lands in the narrow range compatible with galaxy formation and long-lived stars. Our bubble is one of those. The American physicist Steven Weinberg made this argument quantitatively in 1987, before the discovery of dark energy. He predicted, from anthropic reasoning applied to the landscape, that the cosmological constant should be small and positive, and its value should be close to the largest value still compatible with galaxy formation. When dark energy was discovered in 1998, Weinberg's rough prediction bracketed the measured value. It was one of the first successful quantitative predictions using anthropic reasoning in cosmology. This is either deeply impressive or deeply troubling, depending on your perspective. For scientists uncomfortable with the multiverse, the landscape offers no real explanation. Saying our cosmological constant is selected from a distribution of possible values in unobservable universes is to them equivalent to saying it has no explanation at all. The multiverse cannot be observed, tested, confirmed, or falsified by any measurement accessible to us. A theory that accommodates any possible observation by varying parameters across unobservable domains isn't making scientific predictions. It's providing a narrative framework. For scientists who accept the multiverse as a legitimate scientific framework, the predictive success of Weinberg's argument is significant. The landscape predicts a probability distribution over cosmological constant values, weighted by the number of observers each value permits. The observed value falls comfortably within the high probability region of that distribution. That's a successful prediction, even if the mechanism differs from the predictions physicists are used to making. The debate is philosophical as much as scientific, and both sides have serious physicists. What's agreed is this: if no non-anthropic explanation for the dark energy value is ever found, the multiverse will become increasingly difficult to avoid as the framework of last resort. And that prospect has motivated even greater urgency in the search for a dynamical, non-anthropic explanation, a mechanism that selects the dark energy value from first principles, without invoking observers or unobservable domains. That search leads directly to the most speculative and fascinating frontier of current research. Quantum mechanics assigns a wave function to every physical system. The wave function encodes all possible states of the system and their probabilities. For a single electron, the wave function describes where it might be found and what properties it might have when measured. For a hydrogen atom, the wave function describes all possible electron orbitals and their energies. Some physicists have proposed applying this framework to the universe itself. The universe, in this approach, is a quantum system with a wave function, called the wave function of the universe. The entire history of space-time, all its configurations, all its possible expansion histories, all its possible values of physical constants, are encoded in this wave function. James Hartle and Stephen Hawking proposed a specific form for the wave function of the universe in 1983. Their no-boundary proposal says the wave function is determined by a path integral over all compact, smooth four-dimensional geometries with no boundary in the past, so that the universe has no beginning in the way a conventional space-time does. Time itself emerges from the geometry, rather than being a prior framework. In the Hartle-Hawking wave function, the most probable histories of the universe are those that start with the minimum possible initial conditions and expand smoothly. The wave function predicts which values of physical constants are most probable. In principle, it could predict a probability distribution over cosmological constant values. Calculations along these lines are extraordinarily difficult. The path integral over all geometries is not exactly solvable, and approximations are needed. Different approximation schemes give different answers. Some analyses suggest the Hartle-Hawking wave function predicts a large universe with small cosmological constant, which would be consistent with observation. Others suggest it predicts a universe that is overwhelmingly likely to be very small, a near-Planck scale bubble, which seems to contradict what we observe. The wave function of the universe approach is technically immature. The mathematical challenges are severe, but the conceptual framework is compelling. If the universe is a quantum system, its physical constants, including the dark energy value, are not free parameters to be explained externally. They are outcomes of the wave function, as predictable in principle as the energy levels of a hydrogen atom. If the wave function of the universe could be solved exactly, or approximated reliably, it might tell us precisely why the cosmological constant has the value it does. Not because of observer selection, not because of a landscape, but because the quantum state of the universe assigns that value the highest probability, given the boundary conditions of the no-boundary proposal. Whether this is the correct framework is unknown. Whether it produces a unique testable prediction for dark energy is still an open research question. But it represents the most ambitious attempt to give dark energy an explanation that is both quantum and cosmological simultaneously. And it points toward a final realization that runs through every approach we've covered. The question of dark energy is ultimately a question about initial conditions, about why the universe began the way it did, with the constants it has, in the state it was in. The answer to dark energy may be inseparable from the answer to why there is a universe at all. The largest mystery in cosmology might have its answer at the smallest scales physics can probe. Dark energy, whatever it is, sets the energy density of the vacuum, and the vacuum is probed every time a particle physicist runs an experiment. Precision measurements of particle masses, coupling constants, and decay rates are all sensitive to quantum corrections from the vacuum. The vacuum energy, through its contribution to loop diagrams in quantum field theory, shifts these quantities from their bare values to their measured ones. Every precision measurement in particle physics is, in a sense, a measurement of the vacuum. The anomalous magnetic moment of the muon is the most precise measurement in physics. The muon, a heavier cousin of the electron, behaves like a tiny magnet. Its magnetic strength is predicted by quantum field theory to extraordinary precision. Every particle in the theory contributes a tiny correction through virtual processes, briefly appearing and disappearing from the vacuum. The predicted value and the measured value have shown a persistent discrepancy over the past 2 decades at roughly the 4 sigma level. This discrepancy, if real, suggests either a new particle contributing to the vacuum corrections or an error somewhere in the theoretical calculation of known contributions. Either possibility has implications for what the vacuum contains. A new particle, with the right properties to explain the muon anomaly, would also contribute to the vacuum energy, potentially at a level relevant to dark energy. The electron's anomalous magnetic moment shows no discrepancy. The contrast between the muon and electron cases is itself informative. Whatever new physics might exist couples more strongly to heavier particles, which constrains the type of new field it could be. At even smaller scales, neutron scattering experiments and precision atomic spectroscopy tests, where the fundamental constants vary with position or time. If dark energy is a slowly rolling field, it might couple weakly to atomic physics, producing a tiny drift in fine structure constant, the number governing the strength of electromagnetism. Measurements of distant quasar absorption spectra test whether the fine structure constant had the same value billions of years ago as it does today. Current measurements show no variation beyond tight upper limits. Atom interferometers, instruments that use the wave properties of atoms to make exquisitely sensitive measurements of acceleration, are being developed as dark energy detectors. A light scalar dark energy field, with weak coupling to matter, would produce a tiny, position-dependent acceleration that atom interferometers might detect in carefully shielded environments. The signal would look like a subtle deviation from standard gravity at very short ranges, below a millimeter, where the field's effect hasn't been diluted by larger scale averaging. Tabletop experiments at submillimeter scales are already setting the most sensitive limits on any new force at short distances. The physics of dark energy, spread uniformly across the cosmos, might nevertheless leave its most detectable trace at the scale of centimeters and millimeters in a carefully controlled laboratory on Earth. This is the strange upside-down quality of the dark energy problem. The phenomenon itself is cosmological, visible only in the motion of galaxies billions of light years away. But its explanation, if it involves a new field or symmetry, may be most directly tested in a university basement with precision instruments the size of a desk. Physics doesn't progress by philosophy alone, it progresses by measurement. And the next decade will deliver a volume of cosmological data unlike anything previously available. Several experiments, already built or in advanced operation, will together produce the most stringent tests of dark energy theories ever attempted. The Dark Energy Spectroscopic Instrument will complete its 5-year survey, producing three-dimensional maps of tens of millions of galaxies spanning 11 billion years of cosmic history. The baryon acoustic oscillation measurements from this survey will pin down the expansion history of the universe at different epochs with sub-percent precision. If the dark energy equation of state varies by even a few percent from the cosmological constant value, it will show. The Euclid satellite is mapping the shapes of 1 billion galaxies across a third of the sky. Weak gravitational lensing, the subtle distortion of galaxy shapes caused by the mass distribution between them and us, traces how matter clusters under gravity and dark energy. The growth rate of cosmic structure is a direct probe of whether dark energy is dynamical, and Euclid will measure it across cosmic time with unprecedented statistical power. The Vera Rubin Observatory is conducting a decade-long survey of the entire southern sky every few nights. It will discover hundreds of thousands of Type 1a supernovae across a wide range of distances, extending the original measurement that revealed dark energy into a full three-dimensional census. The expansion history inferred from supernovae will cross-check and combine with DAISY and Euclid to break degeneracies between models. The Nancy Grace Roman Space Telescope, expected to launch within the next few years, will survey the infrared sky with a wide field of view, measuring galaxy clustering and weak lensing at high redshifts where the transition from matter domination to dark energy domination occurred. It will extend the observational record to earlier cosmic epochs than current surveys reach. The Simons Observatory and CMB S4 will map the cosmic microwave background with sensitivity sufficient to detect the faint B-mode polarization pattern expected from primordial gravitational waves, and simultaneously constrain the dark energy equation of state through its effect on the growth of cosmic structure. Combining all these measurements, physicists expect to determine the dark energy equation of state and its rate of change to within a few percent. This precision is sufficient to distinguish between a cosmological constant, a slowly rolling quintessence field, an axion-like field, and some classes of modified gravity. If the swampland conjecture is correct, and dark energy is rolling at the rate it predicts, the signal will be visible in the combined dataset. If all experiments converge on a perfect cosmological constant, Equation of state, exactly -1. No variation, no fifth force, no birefringence. Then, the cosmological constant is confirmed as the correct description, and the problem of why it has its precise value becomes the central unsolved question of physics, possibly forever unanswerable without a quantum theory of gravity. If any experiment finds a deviation, a varying equation of state, a cosmic birefringence signal, an equivalence principle violation, the field transforms overnight. A deviation confirms a dynamical dark energy field, constrains its symmetry properties, and gives theorists the specific target they've been missing. Either outcome resolves something, and either outcome leaves deeper questions open. Step back from the equations for a moment. Consider what the existence of dark energy at its measured value has made possible. A universe with a cosmological constant 100 times larger than ours would have expanded too fast for gravity to form galaxies. Dark matter overdensities, the seeds of structure, would have been pulled apart before they could collapse. No galaxies means no stars. No stars means no carbon, no oxygen, no iron. None of the elements that chemistry requires. No chemistry means no biology. No biology means no observers. A universe with a cosmological constant 100 times smaller, but still positive, would look almost identical to ours. Slightly more structure, slightly denser galaxy clusters. Observers would still be possible, but a cosmological constant 1,000 times smaller would create so much structure that galaxies would be cramped, stellar environments chaotic, planetary systems destabilized by stellar encounters. Life-permitting conditions would be rarer, but perhaps not absent. The anthropopically allowed range of cosmological constant values, the range within which observers can exist to measure it, spans roughly 2 orders of magnitude. The value we measure sits near the upper end of that range, which is where Weinberg's anthropic prediction placed it. This correspondence is either the most profound scientific result in history or the most elaborate tautology. We measure the value we measure because we are here, and we are here because the value is what it is. The circle is logically airtight and physically hollow, depending on your view of what physics is supposed to explain. What this stakes out for life in the universe is specific. The dark energy value determines the epoch of structure formation. Structure formation determines when and where stars exist. Stars determine when and where planetary systems exist. The epoch during which complex life can develop is bounded on one side by the time for first-generation stars to produce heavy elements, and on the other side by the increasing hostility of a rapidly expanding, increasingly empty universe. We live in the middle of that window, roughly 10 billion years after the Big Bang, in a galaxy that formed from second-generation stars rich in carbon and oxygen, on a planet orbiting a stable star in a relatively quiet galactic neighborhood. Dark energy's value is why that window exists, why it has the duration it does, and why it's closing. Future civilizations, if they exist and survive, will look up at a sky growing darker as more galaxies recede beyond their horizon. In 1 trillion years, no galaxies outside the local group will be visible. In 10 trillion years, even the local group will be dispersed by dark energy. The night sky will be empty. The physics of dark energy set the timeline for the universe's habitability. Understanding its nature isn't just an abstract scientific quest. It's an account of why conscious beings exist at all, for how long the conditions that allow them persist, and what kind of universe they inhabit. The fact that we are here, asking these questions, during the brief epoch when the universe is structured enough to support us, but not yet too dispersed to observe, that fact is either the deepest coincidence in nature or the most important clue we have. We've traveled from Hubble's telescopes to quantum fields, from the Casimir effect to the string landscape, from phantom energy to the wave function of the universe. Every step has added precision to the question. None has fully answered it. Here is an honest accounting of where we stand. We know dark energy exists. The evidence is overwhelming, independent, and consistent across 4 different measurement methods, spanning decades. Acceleration is real. Something drives it. We know its approximate energy density. It makes up 68% of the total energy content of the universe. Its equation of state is close to -1, the cosmological constant value, within the precision of current measurements. We know the vacuum catastrophe is real. Quantum field theory predicts a vacuum energy roughly 10 to the 123 times larger than what we observe. No accepted mechanism resolves this discrepancy. The problem is open. We know the cosmological constant is the simplest description of dark energy consistent with all current data. Every more complex theory, quintessence, modified gravity, holographic dark energy, is allowed by the data but not required by it. We suspect, from DESI 2204 data, that dark energy may be evolving. The evidence is at the 2 sigma level. It is suggestive and unconfirmed. More data is coming. We don't know if dark energy is a field, a property of space-time, an emergent phenomenon from quantum information, or something that has no name yet. Each possibility is defended by serious physicists with serious arguments. We don't know whether the cosmological constant problem has a solution within known physics, requires new symmetries, requires quantum gravity, or dissolves into anthropic selection. All 4 possibilities remain open. We don't know whether the multiverse is real, whether the string landscape is populated, or whether the anthropic argument is the last refuge of an incomplete theory or the first successful prediction of a correct one. What we know with certainty is that the largest and most pervasive substance in the universe, by a factor of 2 over everything visible, dark and ordinary combined, is the one we understand least. We can calculate its effects to high precision. We cannot say what it is made of, where it comes from, whether it changes over time, or whether it has an explanation in the deepest sense of that word. That's not a failure. That's the frontier. Every major advance in physics began at exactly this kind of boundary, where precise measurements met total theoretical confusion. Newton found gravity, where falling apples met orbital mechanics, and nobody understood why. Einstein found general relativity, where Newton's gravity failed, and light puzzled everyone. Quantum mechanics was born from the ultraviolet catastrophe, an earlier crisis where theory gave a physically impossible prediction for the emission of radiation from a warm object. The vacuum catastrophe, the Hubble tension, the coincidence problem. These are the ultraviolet catastrophe of our time. They are precise, quantitative embarrassments that the current framework cannot absorb. History says they will eventually point the way to a new framework, one that makes dark energy comprehensible the way quantum mechanics made black-body radiation comprehensible. We don't know what that framework looks like. We don't know which of the current proposals is closest to it. We don't know how long it will take to arrive. We know only that when it arrives, it will tell us something true about the deepest structure of reality, about what space is, about what energy is, about why the universe has the future it has rather than none at all. That's worth everything it takes to find it.